two identical twins were born in space, one became paradise, the other became hell. Venus feels completely normal from distance. That's a deadly illusion. Tonight we're discovering how Earth's twin transformed into a furnace that melts metal, and why Earth barely escaped the same fate. Before we explore this planetary nightmare, drop a comment about what scares you most about space. If these cosmic horror stories fascinate you, consider subscribing. These tales of planetary destruction are meant to be shared. Siblings' twin planet origins. Venus and Earth started as cosmic twins, same size, same weight, same rocky guts. 4 billion years ago, something went catastrophically wrong. Venus chose hell while Earth chose life. The measurements reveal this cosmic tragedy perfectly. Both planets formed from the same cloud of rock and metal around our young sun. Venus ended up 95% of Earth's size. That's nearly identical for objects this massive in space. Scientists face what they call the twin planet problem. When two planets start almost exactly the same but end up completely different. Early computer models predicted both worlds should look alike today. Instead, they represent the ultimate sibling rivalry gone wrong. This forces a terrifying question about planetary survival. If Venus could transform from Earth like conditions into a furnace that melts spacecraft, what protects Earth from the same deadly transformation? Transformation solar energy similarity OJ. Venus sits closer to the Sun than Earth. Most people stop there and assume case closed. That assumption misses the real horror completely. Venus gets about twice the solar energy that Earth receives. That sounds like the obvious explanation until you learn something shocking about our own planet's past. Early Earth survived similar energy levels when our Sun burned more intensely. Here's what breaks the simple distance theory. Venus reaches temperatures hot enough to melt copper and lead, about 900 degrees Fahrenheit. Even sitting closer to the Sun, the planet shouldn't get nearly that extreme. Something far more dangerous happened beyond simple solar heating. Scientists call these runaway processes, when small changes trigger bigger changes that keep feeding on themselves. It's like a fire that makes its own wind to burn even hotter. Venus proves that planetary climates can spiral completely out of control. Once these self-feeding cycles start, no planet can stop them or reverse the damage. Extreme environmental contrast. Right now, Venus' surface conditions would kill you in seconds. Earth's surface keeps you perfectly alive. Both planets orbit the same star in the same cosmic neighborhood. The temperature difference between these sister worlds defies belief. Earth maintains liquid water, oceans, and breathable air. Venus creates conditions so extreme that space probes melt before they can land. Venus' atmosphere weighs down with crushing pressure, about 90 times heavier than Earth's air pressing on your body. That's like being squeezed under 3,000 feet of ocean water while standing on dry land. The contrast reveals something terrifying about planetary evolution. Twin planets can follow completely opposite paths even when they start from nearly identical conditions. Earth and Venus prove that planetary climate represents a delicate balance that can tip either toward paradise or hell. Of no-return climate tipping point phenomenon. Planetary atmospheres behave like unstable systems balanced on a knife's edge. Push them slightly in the wrong direction, and they tumble toward extreme conditions. Scientists call these tipping points, moments when gradual change suddenly becomes unstoppable transformation. Venus crossed one of these critical thresholds sometime in its past. Before that moment, the planet could have maintained stable conditions. After crossing the line, Nothing could prevent its transformation into a hellish world. These tipping points work like avalanches in mountains. Small rocks rolling downhill seem harmless until they trigger massive landslides. Small atmospheric changes seem manageable until they trigger planetary transformation. The scariest part involves the one-way nature of these transitions. Once a planet crosses certain thresholds, the processes become irreversible. Venus can never return to Earth-like conditions no matter how much time passes. Balance climate system balance. Earth maintains perfect conditions for life through an intricate web of balancing systems. Ocean currents regulate temperature. Plant life processes carbon dioxide. Ice caps reflect excess heat. All these systems work together like a complex machine. Venus research reveals how easily this planetary machine can break down. When one balancing system fails, it can trigger failures in other systems. Eventually, the entire climate regulation network collapses. Scientists study Venus to understand Earth's climate vulnerabilities. The research shows that our planet's comfortable conditions depend on maintaining delicate equilibrium between competing forces. Small disruptions to this balance could potentially trigger large changes. Venus serves as a cautionary tale about planetary climate stability. It demonstrates that even small changes to atmospheric composition can lead to catastrophic and permanent transformation of entire worlds. Solar radiation energy cycle. What happens when sunlight hits a planet? The energy comes down as visible light. The same light your eyes can see. It warms the planet's surface just like sunlight warms your skin on a summer day. But here's where planetary physics gets dangerous. The heated surface tries to release this energy back to space. It sends the heat away as infrared radiation. Invisible heat rays that you can't see but can feel when you hold your hand near a hot stove. This creates what scientists call the energy cycle. Visible light comes in from the sun. Infrared heat radiation tries to escape back to space. On a normal planet, this cycle balances perfectly. Venus broke this fundamental cycle. The energy still arrives as visible sunlight, but the infrared heat can no longer escape. This transforms a planet's energy system from balanced circulation into a deadly heat trap. Infrared blocking warming. Why can't heat escape from Venus? The answer lies in invisible gases floating in the atmosphere. These gases act like a one-way filter for energy. They let visible light pass through easily but block infrared heat from leaving. Scientists call this the greenhouse effect because it works like glass walls in a greenhouse. Sunlight enters through the glass. The warmed plants inside try to radiate heat back out, but the glass blocks most of that heat from escaping. Greenhouse gases in planetary atmospheres work exactly the same way. Carbon dioxide represents a common greenhouse gas. Water vapor also traps heat effectively. When these gases build up in an atmosphere, they create an invisible ceiling that heat cannot penetrate. The greenhouse effect explains why Venus became a furnace while Mars froze into a desert. Venus accumulated too many heat-trapping gases. Mars lost most of its atmospheric gases entirely. Greenhouse effect necessity and danger. Earth would freeze solid without greenhouse gases. Remove all the carbon dioxide and water vapor from our atmosphere, and average global temperatures would plummet to -18 degrees Fahrenheit. That's cold enough to freeze the entire surface of our planet. Greenhouse gases create a delicate thermostat effect for planetary climates. Just the right amount keeps Earth warm enough for liquid water and life. Too little greenhouse effect and planets freeze. Too much and planets turn into ovens. Venus demonstrates what happens when this natural thermostat breaks down completely. The planet accumulated so many greenhouse gases that heat became permanently trapped. No cooling mechanism could overcome the massive heat-trapping effect. This reveals the razor-thin margin between life and death for planetary climates. The same gases that make Earth habitable can destroy a planet when they accumulate beyond critical thresholds. Atmospheric density positive feedback hack. Denser atmospheres trap more heat than thin ones. This seems obvious until you realize it creates a vicious cycle that can destroy entire worlds. Scientists call this positive feedback, when one change triggers more changes in the same direction. Here's how the cycle works on Venus. More greenhouse gases make the atmosphere thicker. Thicker atmosphere traps more heat. Higher temperatures release even more greenhouse gases from rocks and other sources. These additional gases make the atmosphere even thicker. The process feeds on itself like a growing wildfire. Each step makes the next step stronger. Once this cycle starts, no natural process can stop it or reverse the damage. Venus got caught in this unstoppable heating spiral billions of years ago. The planet's atmosphere became 90 times denser than Earth's atmosphere. This crushing density ensures that heat can never escape back to space. Radiation balance collapse. Every stable planet maintains energy balance. Energy coming in from the sun equals energy radiating back to space. When this balance breaks, planetary climates spiral toward extreme conditions that can never return to normal. Venus crossed the point where incoming solar energy permanently exceeded outgoing heat radiation. Scientists call this radiation imbalance. Once this threshold gets crossed, temperature keeps rising until it reaches a new and deadly equilibrium. The scary part involves the permanent nature of this collapse. Even if Venus somehow lost all its greenhouse gases tomorrow, the planet couldn't return to Earth-like conditions. Too many irreversible changes have already occurred. This radiation balance represents the ultimate climate control system for planets. When it fails, worlds transform into environments so extreme that they can never support life again. Venus' atmosphere contains almost nothing but carbon dioxide. 96% of every breath would be pure carbon dioxide, the same gas that bubbles out of soda and makes bread rise. Earth's atmosphere contains less than 0.5% carbon dioxide. Venus' atmosphere weighs down with nearly pure carbon dioxide from ground level to space. This represents 10,000 times more heat-trapping gas than Earth's entire atmosphere. The massive carbon dioxide concentration creates what scientists call a super greenhouse effect. Each molecule of carbon dioxide acts like a tiny heat trap floating in the air. When you have trillions of these molecules packed into every cubic inch of atmosphere, they create an impenetrable blanket of heat retention. This gas dominance explains why Venus became a furnace instead of a garden. The planet accumulated so much carbon dioxide that no other atmospheric process could compete with its heat-trapping power. Venus clouds contain concentrated sulfuric acid. This represents the same chemical that car batteries use, except much stronger and floating 30 miles above the planet's surface. These acid clouds form through a hellish chemical process. Volcanic sulfur gases rise into the atmosphere. Solar radiation breaks apart these molecules and recombines them into sulfuric acid droplets. The droplets cluster into permanent cloud layers that completely hide the planet's surface. The acid concentration measures stronger than any acid you could buy in a chemical supply store. These clouds would dissolve metal, plastic, and human tissue within seconds of contact. Yet the clouds never rain down to the surface because the lower atmosphere stays too hot for liquid droplets to survive. Venus created the only known planetary system where acid rain forms constantly but never reaches the ground. The drops evaporate in the scorching lower atmosphere before they can fall more than a few miles. Standing on Venus' surface feels like being crushed under 90 atmospheres of pressure. Scientists measure atmospheric pressure in units called atmospheres. Venus registers 90 times heavier than Earth's air pressure. This crushing weight creates conditions similar to being underwater at depths where submarines start to implode. The dense atmosphere presses down on every square inch with the force of a large truck. No human-built structure could withstand this crushing pressure without massive engineering. The extreme pressure changes how heat moves through the atmosphere. Dense gases conduct heat more efficiently than thin gases. This means Venus's crushing atmosphere spreads heat evenly across the entire planet's surface, preventing any cool spots from forming. Venus' atmosphere achieved density levels that transform gas into something almost like liquid. The boundary between Venus's atmosphere and surface becomes blurred because the air acts more like thick fluid than normal gas. A Venus atmosphere contains almost no water vapor, less than 20 parts per million. Imagine trying to fill a swimming pool with just 20 drops of water spread throughout the entire volume. Earth's atmosphere holds thousands of times more water vapor than Venus's bone-dry air. This represents one of the most dramatic differences between the two planets. Water vapor acts as both a greenhouse gas and a cooling agent through cloud formation and rain cycles. The tiny amount of water vapor that does exist in Venus' atmosphere contributes to the greenhouse heating. Water molecules trap infrared heat, just like carbon dioxide molecules. Even these trace amounts add extra heat retention to an already overheated system. Venus lost its water through a process scientists call atmospheric escape. The intense heat broke water molecules apart into hydrogen and oxygen. The lightweight hydrogen escaped to space while oxygen reacted with surface rocks and disappeared from the atmosphere permanently. Sulfur chemicals dominate Venus' atmospheric chemistry. These compounds create reactions that would be impossible on Earth because our atmosphere lacks the extreme heat and pressure needed to drive such violent chemistry. Sulfur dioxide gas rises from volcanic activity and reacts with trace amounts of water vapor to form sulfuric acid. Solar ultraviolet radiation breaks apart sulfur compounds and recombines them into dozens of different poisonous chemicals that cycle through the atmosphere. The sulfur chemistry creates a self-sustaining cycle of acid production. Volcanoes release sulfur gases. Atmospheric reactions convert these gases into acids. The acids attack surface rocks and release more sulfur compounds back into the air. Venus developed the solar system's most corrosive atmospheric environment through this sulfur-dominated chemistry. The planet maintains chemical conditions so extreme that they would instantly destroy any Earth-based life form or human technology exposed to them. Life impossible extreme heat. No Earth creature could survive Venus' surface heat for even 1 second. The temperature reaches 900 degrees Fahrenheit, hot enough to melt zinc, lead, and tin right out of solid metal objects. Scientists have tested the most heat-resistant bacteria ever discovered on Earth. These microscopic organisms live in boiling hot springs and underwater volcanic vents. Even these extreme survivors would die instantly on Venus' surface. The temperature stays constant everywhere on the planet. Day or night, North Pole or South Pole, the mercury never drops below this deadly threshold. Venus maintains surface conditions that exceed the melting point of many common metals. This extreme heat creates what biologists call a sterile environment, a place where no biological process can function. Venus' surface temperatures destroy the chemical bonds that hold proteins and DNA together, making any form of life impossible. Dissolves sugar. Extreme acidic corrosive environment. Everything dissolves in Venus' atmosphere. The sulfuric acid concentration measures stronger than acid used in car batteries, except this acid floats everywhere as invisible vapor. Battery acid can burn through human skin and metal within minutes. Venus atmospheric acid works hundreds of times faster than battery acid. It would dissolve aluminum, steel, and copper faster than you could watch it happen. The acid doesn't just float in the clouds above. It penetrates every layer of the atmosphere from ground level to space. Nothing escapes contact with this corrosive environment that attacks every material known to science. Venus created the most chemically aggressive environment in our solar system through its acid-saturated atmosphere. Even spacecraft built with the strongest materials survive only hours before the acid dissolves their protective systems completely. Extreme day cycle uniform temperature. Venus days stretch longer than most planets' years. One complete day-night cycle on Venus equals 243 Earth days. Almost 8 months of continuous sunlight followed by 8 months of darkness. You might expect such long nights to cool the planet down significantly. Instead, Venus' surface temperature never changes by more than a few degrees between day and night. The thick atmosphere spreads heat so evenly that darkness cannot provide relief. This happens because Venus' atmosphere acts like a giant heat-spreading blanket. The dense gases move heat from the day side to the night side faster than the surface can cool down. Heat distribution happens faster than heat loss to space. Venus proves that planetary temperature depends more on atmospheric thickness than on day-night cycles. Even eternal darkness cannot cool a planet once its atmosphere becomes thick enough to distribute heat efficiently across the entire surface. Air races like hurricane, dual atmospheric circulation. Venus' atmosphere moves in two completely different speed zones. Surface winds crawl slower than a gentle breeze on Earth. Upper atmospheric winds race faster than the strongest hurricanes ever recorded. Near the ground, air barely stirs at walking pace speeds. These surface winds move so slowly they couldn't even blow dust around effectively. The crushing atmospheric pressure and extreme density create conditions where air movement becomes sluggish and stagnant. 50 miles above the surface, the same atmosphere transforms into racing superhighways of wind. These upper winds complete a trip around the entire planet in just 4 Earth days. That means atmospheric gases travel faster than jet aircraft in Earth's sky. Venus created a planetary wind system unlike anything else in our solar system. A 2-layer atmosphere where the bottom stays nearly motionless while the top races at incredible speeds around the globe. Permanent twilight state. What would you see if you could stand on Venus' surface and look up? Not the sun, not blue sky, not even normal clouds. The thick acid cloud layers block almost all direct sunlight from reaching the ground. Scientists estimate that Venus' surface receives about as much light as Earth gets during a heavy thunderstorm, even at midday with the sun directly overhead. This creates what planetary scientists call perpetual twilight conditions. Enough light penetrates the clouds to see your surroundings, but everything appears dim and orange-tinted, like sunset light filtered through heavy pollution. Venus' surface exists in permanent shadow despite receiving intense solar radiation above its clouds. The planet's own atmosphere has become so thick and toxic that it blocks out the very star that powers its hellish greenhouse effect. Early Venus might have enjoyed pleasant weather for billions of years. Scientists studying stellar evolution have discovered something unexpected about our sun's past behavior that changes everything we thought about Venus's doomed climate. 4 billion years ago, our sun burned much dimmer than it does today. This phenomenon happens to all stars. They gradually increase their energy output as they age. The young sun produced only 70% of its current energy output during Venus's early history. Reduced solar energy means early Venus received much less heat than the scorching radiation it endures today. This lower energy input could have allowed the planet to maintain temperatures suitable for liquid water oceans and stable weather systems. Venus's transformation into hell might represent a recent development rather than an ancient condition. The planet could have maintained Earth-like conditions for most of its existence before crossing the tipping point that led to runaway greenhouse heating. Could Venus have supported liquid water oceans? Advanced climate modeling suggests the answer might shock you. Yes, under the right conditions. Scientists run computer simulations that recreate Venus's early atmospheric conditions. These models test different combinations of atmospheric gases, cloud cover, and solar energy levels. Some simulation results show stable liquid water persisting on Venus' surface for billions of years. The key factor involves finding the right balance between greenhouse heating and cooling effects. Too little greenhouse effect, and the planet freezes. Too much, and it turns into the furnace we see today. But computer models identify a narrow sweet spot where early Venus could have maintained perfect temperatures. These simulations prove that Venus's hellish conditions weren't inevitable from the moment of planetary formation. The planet had realistic chances of developing and maintaining habitable surface conditions throughout most of its history. Venus's slow rotation creates the longest days in our solar system. One Venus day equals 243 Earth days, longer than a Venus year itself. Most scientists assumed this extreme rotation would make the planet uninhabitable. But slow rotation combined with thick cloud cover might have created perfect climate control instead of climate chaos. The clouds reflect enormous amounts of solar energy back to space. Scientists call this the albedo effect, where bright surfaces bounce sunlight away. Early Venus could have achieved a delicate balance between two competing effects. Greenhouse gases trapped some heat to warm the planet. Meanwhile, reflective clouds excess heat back to space to prevent overheating. This natural thermostat could have maintained stable temperatures. Venus's current clouds still reflect most incoming solar energy, but the greenhouse effect has become so powerful that even this massive cooling system cannot prevent surface temperatures from reaching deadly extremes. What if early Venus breathed different air? Scientists studying planetary formation suggest Venus's original atmosphere might have contained completely different gases than the carbon dioxide-dominated hellscape that exists today. Early planetary atmospheres often contain more nitrogen and water vapor with much less carbon dioxide. Nitrogen acts as a neutral gas that doesn't trap heat like carbon dioxide does. Water vapor creates cooling effects through cloud formation and rain cycles. This alternate atmospheric recipe could have prevented Venus from developing its deadly super greenhouse effect. The planet might have maintained moderate greenhouse warming without crossing into runaway heating that destroys all cooling mechanisms. Venus's current atmosphere represents the end result of billions of years of atmospheric evolution, not necessarily the starting conditions. The planet's original air might have been as suitable for life as Earth's early atmosphere before chemical processes transformed it into today's toxic mixture. Giant asteroid impacts and massive volcanic eruptions don't just damage planets temporarily. These catastrophic events permanently alter atmospheric chemistry in ways that can push entire worlds toward uninhabitable conditions. Venus experienced bombardment from space rocks and volcanic activity throughout its early history. Each major impact vaporized surface rocks and released buried gases into the atmosphere. Each volcanic eruption pumped additional greenhouse gases into the air. Scientists study how these events gradually shifted Venus's atmospheric composition toward more carbon dioxide and less water vapor. Like drops filling a bucket, each catastrophic event added more heat-trapping gases until the atmosphere reached a critical threshold. Venus crossed the tipping point where cooling mechanisms could no longer balance heating effects. Once this threshold was crossed, the planet's fate was sealed regardless of whether future impacts or eruptions occurred. Venus water began destroying itself through a process that feeds on its own success. When water evaporates into the atmosphere, it becomes water vapor, an invisible gas that traps heat just like carbon dioxide does. This creates what scientists call positive feedback. One change causes more of the same change to happen. More water evaporation means more heat-trapping vapor in the air. More heat-trapping vapor means higher temperatures. Higher temperatures cause even more water to evaporate. The process works like a snowball rolling downhill that gets bigger and bigger as it rolls. Once Venus crossed the threshold where evaporation exceeded condensation, the feedback loop became unstoppable. Each molecule of water vapor made the next molecule easier to evaporate. Venus oceans literally boiled themselves out of existence through this self-amplifying process. The planet's water supply became the fuel for its own atmospheric destruction, creating a cycle that no natural cooling process could interrupt or reverse. High in Venus's atmosphere, water molecules cannot survive the intense solar radiation. Ultraviolet light from the sun acts like molecular scissors, cutting water molecules apart into their basic components, hydrogen and oxygen atoms. Once separated, these atoms follow completely different paths to permanent disappearance. Hydrogen represents the lightest element in the universe, making it easy for this gas to escape Venus's gravitational pull and drift away into space forever. Oxygen atoms face a different fate, but equally permanent removal from the atmosphere. These heavier atoms cannot escape to space easily, so they fall back down to the planet's surface. There they react with iron and other metals in rocks, forming rust-like compounds that lock the oxygen away permanently. Venus lost its water through this two-step molecular destruction process. The hydrogen escaped to space, while the oxygen became chemically bound in surface rocks, ensuring that water molecules could never reform even if the planet somehow cooled down later. Water has a secret temperature limit that most people never learn about. Scientists call this the critical temperature. It is the point where water cannot exist as a liquid no matter how much pressure gets applied to it. On Earth, water boils at different temperatures depending on pressure. In low-pressure mountain air, water boils at lower temperatures. In high-pressure deep ocean conditions, water stays liquid at much higher temperatures. But every substance has an absolute limit where pressure cannot prevent boiling. Venus' surface temperature exceeds water's critical temperature of 705 degrees Fahrenheit. Above this threshold, water exists only as vapor regardless of atmospheric pressure. Even Venus's crushing atmospheric pressure cannot force water molecules to condense into liquid form. This temperature barrier explains why Venus can never develop oceans again, even if it somehow acquired new water. The planet's surface conditions have permanently crossed into the temperature zone, where liquid water becomes physically impossible under any circumstances. Venus' atmosphere reached a point where evaporation continues but condensation becomes impossible. This breaks the fundamental water cycle that operates on every planet with liquid water, the endless process of evaporation, cloud formation, and precipitation. Normal planetary water cycles work like giant recycling systems. Ocean water evaporates into the atmosphere. The water vapor condenses into clouds. The clouds release water back to the surface as rain or snow. This cycle has operated on Earth for billions of years. Venus crossed the threshold where atmospheric conditions prevent the condensation step from occurring. Water continues to evaporate from any remaining surface sources, but the vapor cannot condense back into droplets because the atmosphere stays too hot and dense. Once the water cycle breaks down completely, planets lose their primary mechanism for cooling and climate regulation. Venus' atmosphere became a one-way system where water enters as vapor but can never return to the surface as liquid precipitation. After Venus's last ocean evaporated completely, the planet crossed into a state that scientists call irreversible atmospheric evolution. Changes this extreme cannot be undone by any natural process, even given billions of years. The complete removal of liquid water eliminated Venus's primary cooling and climate regulation system. Oceans act like planetary air conditioners. They absorb heat, distribute it globally through currents, and release it gradually. Without this cooling system, planets cannot maintain moderate temperatures. Venus' surface today shows little direct evidence that oceans ever existed. The water disappeared so completely that even geological features created by ancient seas have been erased by volcanic activity and atmospheric erosion over millions of years. This represents the most permanent type of planetary change possible. Environmental transformation so complete that the planet cannot return to its original state even if external conditions change. Venus lost the capacity for oceans forever, regardless of how its atmosphere or solar radiation might evolve in the future. Still uses today. Carbon cycle regulation disappearance (ED). Earth maintains stable air composition through a natural recycling system that Venus lost forever. This system works like a planetary thermostat. When too much carbon dioxide builds up in the air, Earth's oceans absorb the excess gas and store it safely underwater. Ocean water acts like a giant sponge for carbon dioxide. The gas dissolves into seawater, just like sugar dissolves into coffee. Marine creatures use this dissolved carbon dioxide to build shells and skeletons. When these organisms die, they sink to the ocean floor and lock the carbon away for millions of years. Venus had no oceans to absorb excess carbon dioxide once its water disappeared. Without this natural absorption system, greenhouse gases could only accumulate in the atmosphere with no removal mechanism. The planet lost its primary method for controlling atmospheric composition. Earth's carbon cycle represents a critical planetary life support system that prevents runaway greenhouse effects. Venus demonstrates what happens when planets lose this natural air purification and temperature regulation system completely. Weathering blockade. On Earth, rocks slowly dissolve in rainwater and consume carbon dioxide from the atmosphere. This process happens so gradually that most people never notice it, but it removes enormous amounts of greenhouse gas over geological time periods. Rock weathering works like a planetary vacuum cleaner for carbon dioxide. Rainwater becomes slightly acidic when it absorbs carbon dioxide from the air. This weak acid dissolves certain types of rocks and minerals. The chemical reactions consume atmospheric carbon dioxide and convert it into harmless compounds. Venus' surface receives no rainfall to drive these carbon-removing chemical reactions. Without liquid water, the planet cannot operate the rock weathering process that slowly cleans carbon dioxide out of planetary atmospheres. The rocks remain chemically inactive. Venus lost access to one of the universe's most effective long-term methods for removing greenhouse gases from planetary atmospheres. Rock weathering represents a natural air cleaning service that requires liquid water to function properly. Carbon dioxide accumulation. Venus volcanoes continue pumping carbon dioxide into the atmosphere while no natural process removes it. This creates what scientists call a one-way system. Gases enter the atmosphere but never leave it. Volcanic activity operates like a massive industrial gas factory that runs continuously without environmental controls. Every eruption releases stored carbon dioxide from deep within the planet. On Earth, natural removal processes balance this volcanic input. On Venus, nothing counteracts the constant gas production. The atmospheric composition shifts dramatically when input exceeds output for millions of years. Venus' atmosphere became increasingly dominated by carbon dioxide because volcanoes kept adding more while no mechanism eliminated any. The planet developed a severe atmospheric imbalance. Venus created the ultimate environmental disaster scenario: unlimited pollution production with zero cleanup capability. This one-way accumulation process transformed the planet's air into a toxic greenhouse gas concentration that no natural system can reduce. Atmospheric disaster. Carbonate formation impossibility. Earth stores massive amounts of carbon in limestone and other carbonate rocks. These rocks form when carbon dioxide dissolved in ocean water combines with calcium and other minerals. The process creates solid rock that locks carbon away from the atmosphere permanently. Carbonate rock formation requires liquid water to operate effectively. Ocean chemistry facilitates the reactions that convert dissolved carbon dioxide into solid mineral deposits. This represents one of Earth's most important long-term carbon storage mechanisms. Venus cannot form carbonate rocks without liquid water to drive the necessary chemical processes. The planet lacks the basic ingredient needed to convert atmospheric carbon dioxide into solid storage compounds. Carbon remains trapped in the atmosphere indefinitely. Earth uses carbonate rock formation to bury billions of tons of atmospheric carbon safely underground. Venus demonstrates what happens when planets lose access to this crucial carbon storage system that prevents permanent atmospheric contamination. Carbon storage singularization. Venus' atmosphere became the planet's only carbon storage location. On Earth, carbon gets distributed among multiple reservoirs: atmosphere, oceans, rocks, and living organisms. Venus lost all storage options except its increasingly dense atmosphere. Healthy planetary carbon systems work like investment portfolios. They spread carbon among different storage locations to maintain balance. When one storage system becomes overloaded, others can absorb the excess. This diversification prevents any single reservoir from becoming dangerously concentrated. Venus lost its carbon storage diversity when water disappeared and volcanic activity intensified. The atmosphere became a single massive carbon reservoir with no backup systems. All the planet's carbon accumulated in one place with no alternative storage options available. This storage centralization explains why Venus cannot reverse its greenhouse effect through natural processes. The planet's carbon management system collapsed into a single overloaded reservoir that cannot redistribute its contents to other storage locations. Venus cannot cool down because heating creates more heating. Scientists call this a positive feedback loop, when the result of a process makes that same process happen even more intensely. Imagine a microphone placed too close to a speaker. The microphone picks up sound from the speaker. The speaker amplifies that sound and sends it back to the microphone. Each cycle gets louder until the system produces an ear-splitting screech that drowns out everything else. Venus' atmosphere works exactly like that microphone feedback loop. Higher temperatures create more greenhouse gases. More greenhouse gases trap more heat. More trapped heat creates even higher temperatures. Each step amplifies the next step until the process spirals completely out of control. Once positive feedback loops reach a certain intensity, no external force can stop them from continuing. Venus crossed the threshold where cooling mechanisms became too weak to interrupt the self-amplifying heating process that now defines the planet's climate permanently. Water vapor creates the most vicious heating spiral in planetary atmospheres. When temperatures rise, air can hold much more invisible water vapor, just like how hot air in your bathroom holds more steam after a shower than cold air can contain. Atmospheric scientists have discovered that water vapor acts as a more powerful greenhouse gas than carbon dioxide. Every degree of temperature increase allows the atmosphere to absorb exponentially more water vapor. This additional water vapor traps dramatically more heat than the original temperature increase. The process feeds on itself with mathematical precision. Scientists call this exponential amplification, where small changes produce increasingly larger effects. A 2-degree temperature increase might allow 4 times more water vapor. 4 times more water vapor might cause 8 degrees of additional heating. Venus water vapor feedback created heating acceleration that overwhelmed every natural cooling mechanism on the planet. The process transformed gradual climate change into explosive atmospheric transformation that occurred faster than geological systems could adapt. Bright planetary surfaces reflect solar energy back to space like mirrors bouncing light away. Dark surfaces absorb solar energy and convert it to heat like black pavement on summer days. Venus lost its bright reflective surfaces and gained dark heat-absorbing areas. Ice caps and bright clouds normally cool planets by reflecting enormous amounts of incoming solar radiation. When these reflective surfaces shrink or disappear, planets absorb much more energy from their parent star. The extra absorbed energy raises temperatures further. Higher temperatures eliminate even more bright reflective surfaces in an accelerating cycle. Melting ice exposes dark land underneath. Changing atmospheric chemistry reduces bright cloud coverage. Each loss of reflective surface area accelerates the heating process. Venus' atmosphere became so hot and dense that reflective surfaces could no longer form or persist. The planet developed maximum solar energy absorption with minimum energy reflection, creating the most efficient heat collection system possible for a rocky world. Extreme atmospheric heating destroys the very mechanisms that planets use to cool down. Venus lost its natural air conditioning systems precisely when it needed them most to prevent catastrophic overheating. Planetary cooling depends on gases escaping to space from the upper atmosphere. Intense heating causes atmospheric expansion that makes gas molecules move faster and reach higher altitudes. Paradoxically, this expansion reduces the atmosphere's cooling efficiency instead of improving it. Hot expanded atmospheres become less dense at high altitudes where cooling normally occurs. lower density reduces the rate of heat radiation to space. The atmosphere retains more heat even as it grows larger and seemingly more capable of cooling. Venus' upper atmosphere expanded so dramatically under extreme heating that it lost most of its capacity to radiate heat away to space. The planet's cooling systems failed at exactly the moment when cooling became most critical for preventing runaway climate change. Venus passed the point where no amount of cooling could restore normal planetary climate. Scientists studying extreme greenhouse effects have identified critical temperature thresholds beyond which planets cannot return to their original atmospheric states. These climate transition points work like eggs cooking in boiling water. Once the proteins change their molecular structure, no amount of cooling can turn them back into raw eggs. Planetary atmospheres undergo similar irreversible chemical and physical changes under extreme conditions. Venus crossed multiple irreversible thresholds simultaneously. Water molecules decomposed permanently. Surface rocks underwent chemical changes that prevent atmospheric carbon storage. Volcanic activity intensified beyond sustainable levels. Each change made recovery more impossible. The planet reached what climate scientists call a new stable state. Atmospheric conditions so extreme that they represent permanent equilibrium rather than temporary disruption. Venus cannot return to Earth-like conditions even if given billions of years to cool naturally. Stacked on top of each other. Altitude environmental differences. Venus' atmosphere contains multiple planets' worth of different environments layered like floors in a skyscraper. Ground level feels like the inside of a blast furnace. 50 miles up feels like a pleasant spring day on Earth. Scientists mapping Venus' vertical atmosphere discovered that climbing through the air produces more dramatic environmental changes than traveling from Earth's equator to its poles. Each mile of altitude creates completely different living conditions on the same planet. Temperature drops from 900 degrees at surface level to comfortable room temperature in the upper clouds. Atmospheric pressure decreases from bone-crushing intensity to levels that humans could survive with basic breathing equipment. The chemical composition shifts from toxic soup to relatively harmless gas mixtures. Venus demonstrates that planetary environments exist in 3 dimensions rather than just across surface geography. The planet contains multiple climate zones stacked vertically, creating the most extreme atmospheric diversity in our solar system within a single world. Pressure convection suppression. A Venus surface atmosphere weighs so much that air behaves more like thick fluid than normal gas. This crushing density prevents the natural air circulation that helps cool most planetary surfaces. Normal atmospheric convection works like boiling water in a pot. Hot air rises from heated surfaces. Cool air sinks from higher altitudes. This circulation mixes hot and cold air masses to distribute temperature evenly across planetary surfaces. Venus' surface pressure reaches 90 times Earth's atmospheric weight, equivalent to being underwater at depths where submarines become dangerous to operate. Under such crushing pressure, heated air cannot rise effectively because the surrounding air pushes back with enormous force. The suppressed convection traps hot air near the surface where it cannot escape to cooler altitudes. Venus' surface remains uniformly scorching because atmospheric mixing becomes physically impossible under extreme pressure conditions. Cloud-stable layer. Venus maintains a permanent chemical manufacturing zone 30 miles above its surface. This altitude provides perfect temperature and pressure conditions for continuous sulfuric acid cloud production that operates 24 hours a day. The cloud formation zone works like an industrial chemical plant suspended in mid-air. Raw materials rise from volcanic activity below. Solar radiation provides energy for chemical reactions. The precise altitude creates ideal temperature for sulfuric acid droplets to form and persist. These clouds never dissipate because atmospheric conditions at 30-mile altitude remain constantly favorable for acid production. Unlike Earth clouds that form and disappear based on weather patterns, Venus clouds represent permanent atmospheric features. Venus created the solar system's most stable cloud layer through precise atmospheric chemistry that maintains constant acid cloud production at optimal altitude. This represents a self-sustaining chemical factory that requires no external maintenance to continue operation. Zone. A Venus upper atmosphere contains the most Earth-like conditions found anywhere else in our solar system. 50 miles above the hellish surface. Temperature and pressure approximate pleasant autumn weather on Earth. Atmospheric scientists have identified what they call the habitable zone of Venus. Altitude ranges where humans could survive, with basic life support equipment rather than the heavy-duty protection needed for surface exploration. Temperature stays around room temperature levels. Pressure remains manageable for human physiology. Space agencies seriously study floating research stations that could operate in this mild upper atmosphere. These aerial platforms would hover above the toxic lower atmosphere while enjoying relatively benign environmental conditions for extended human presence. Venus' upper atmosphere proves that habitable environments can exist in unexpected locations throughout our solar system. The planet offers accessible research opportunities despite its surface representing one of the most hostile environments known to science. Temperature gradient circulation limitation. Venus' atmosphere traps hot air near the surface through an inverted temperature structure that prevents normal atmospheric circulation. Hot, dense air cannot rise through even hotter, dense air above it. Normal planetary atmospheres cool with altitude. Like climbing a mountain where air gets colder the higher you go. This temperature gradient allows hot surface air to rise toward cooler upper levels. Venus' atmosphere maintains nearly constant temperature throughout its lower layers. Without significant cooling at higher altitudes, heated surface air has nowhere cooler to rise toward. The atmosphere loses its natural circulation mechanism that normally distributes heat vertically. Hot air accumulates near the surface with no escape route upward. This temperature gradient creates what atmospheric physicists call circulation stagnation, when atmospheric layers become isolated from each other and cannot exchange heat effectively. Venus' surface heat remains permanently trapped in the lowest atmospheric zone, where it continues to accumulate. Venus volcanoes released more greenhouse gases in single eruptions than entire civilizations produce in centuries. Each major volcanic explosion pumped massive quantities of carbon dioxide and sulfur compounds directly into the atmosphere, with no natural cleanup system to remove them. Volcanic eruptions work like giant underground pressure cookers that finally burst open. Molten rock contains dissolved gases under enormous pressure. When magma reaches the surface, these compressed gases expand explosively and escape into the atmosphere at volumes impossible to imagine. Earth's volcanoes also release greenhouse gases, but Earth's oceans and rock weathering systems absorb most of the emissions over time. Venus lost these natural absorption mechanisms, so every gas molecule released by volcanoes remained permanently in the atmosphere. Venus volcanoes transform from temporary geological events into permanent atmospheric pollution sources. Each eruption added to an ever-growing concentration of heat-trapping gases that could never be removed by natural processes. Venus cannot release internal heat through gradual surface processes because the planet lacks the geological conveyor belt system that keeps Earth's crust moving. Scientists call this system plate tectonics, where large sections of planetary crust slowly drift and recycle over millions of years. Without plate tectonics, Venus traps underground heat until pressure builds to catastrophic levels. The planet accumulates thermal energy like a sealed pressure cooker with no safety valve. Eventually, the accumulated pressure must escape through massive volcanic episodes. These global volcanic events happen simultaneously across the entire planet, rather than gradually at different locations like Earth experiences. Venus undergoes what geologists call resurfacing events, when volcanic activity erupts everywhere at once and literally rebuilds the entire planetary surface. Venus' geological system operates through catastrophic episodes rather than gradual change. The planet alternates between periods of relative calm and explosive periods when underground pressure overwhelms surface stability everywhere simultaneously. Massive lava floods covered most of Venus's surface with volcanic rock during the planet's most recent geological upheaval. These eruptions released the gases that created Venus's current toxic atmosphere, while simultaneously erasing evidence of previous surface conditions. Basalt eruptions work differently from explosive volcanoes that shoot material high into the air. Instead, liquid rock flows across vast distances like slow-moving rivers of molten stone. These lava flows can cover areas larger than entire countries before cooling into solid rock. Venus lava floods released enormous volumes of volcanic gases because the eruptions continued for millions of years across huge geographic areas. Each flowing lava river contributed additional greenhouse gases to the atmosphere, while the flowing rock buried previous surface features. The current Venus surface represents a relatively recent geological creation that erased most evidence of the planet's earlier history. These massive lava floods simultaneously built the modern landscape and poisoned the atmosphere beyond any hope of recovery. Venus volcanic gases contain unusually high concentrations of sulfur compounds compared to Earth's volcanic emissions. These sulfur-rich gases create the raw ingredients for Venus's acid cloud production and corrosive atmospheric chemistry. Sulfur gases behave like poisonous cooking ingredients that create toxic recipes when mixed together in planetary atmospheres. Sulfur dioxide combines with water vapor to form sulfuric acid. Solar radiation breaks sulfur compounds apart and recombines them into dozens of corrosive chemicals. Venus volcanoes act like massive chemical factories that specialize in producing the most corrosive atmospheric ingredients possible. The planet's unique geological chemistry favors sulfur-rich volcanic emissions that Earth's volcanoes rarely produce in comparable quantities. This sulfur-dominated volcanic chemistry explains why Venus developed such an aggressively corrosive atmosphere. The planet's volcanoes literally cook up the most toxic atmospheric recipes possible using sulfur as the primary poisonous ingredient. Venus underwent a complete planetary renovation approximately 500 million years ago that transformed both its surface geology and atmospheric composition. This global resurfacing event represents one of the most dramatic geological transformations known in our solar system. Planetary resurfacing works like demolishing and rebuilding an entire city at the same time. Volcanic activity melted and reformed the planet's outer shell while releasing all the gases trapped in surface rocks. This geological renovation project lasted millions of years and affected every square mile of planetary surface. The timing suggests this resurfacing event created Venus's current hellish atmosphere rather than existing from the planet's formation. Before this geological catastrophe, Venus might have maintained very different atmospheric conditions that supported moderate temperatures. Venus demonstrates that planetary climate can change catastrophically through geological processes that operate over timescales much longer than human experience. Single geological events can permanently alter entire world environments in ways that make previous conditions impossible to restore. Solar luminosity increases fate. Our sun gets brighter as it ages, unlike human expectations that stars should burn out and grow dimmer over time. This stellar aging process gradually increases the energy output that reaches every planet in our solar system. Scientists studying stellar evolution have discovered that stars like our sun increase their energy production by about 10% every billion years. This happens because nuclear fusion in the star's core becomes more efficient as the star accumulates helium from hydrogen burning. Venus might have maintained comfortable temperatures when the sun produced less energy billions of years ago, as solar energy gradually increased over geological time. Venus received more and more heat until it crossed the threshold that triggered runaway greenhouse effects. The sun's inevitable brightening process means Venus was always destined to become uninhabitable eventually. Even if the planet had maintained perfect early conditions, stellar evolution would have ultimately pushed it beyond the limits of climate stability. Solar wind atmospheric selective removal. Solar wind constantly strips away planetary atmospheres through a process that works like invisible sandblasting from space. Our sun continuously shoots streams of charged particles that hit planetary atmospheres and knock gas molecules away from their parent planets. Young stars produce much more intense solar winds than older mature stars. Early in our solar system's history, the sun blasted Venus and other planets with solar wind intensities far beyond current levels. These powerful particle streams selectively removed lighter atmospheric gases. Solar wind affects different atmospheric gases unequally based on their molecular weights. Lightweight gases like hydrogen and helium get swept away easily. Heavy gases like carbon dioxide resist solar wind removal and accumulate in planetary atmospheres over time. Venus lost its lighter atmospheric components to intense early solar wind while retaining heavy greenhouse gases like carbon dioxide. This selective atmospheric removal process helped concentrate the heat-trapping gases that eventually created Venus's extreme greenhouse effect. Destroys Venus's water ultraviolet atmospheric chemical control. Ultraviolet radiation from the sun breaks apart water molecules in planetary upper atmospheres like molecular scissors cutting chemical bonds. This process happens constantly in Venus's atmosphere but rarely affects Earth's water supply. Earth's ozone layer blocks most solar ultraviolet radiation before it can reach our planet's water vapor. Venus lacks this protective ozone shield, so ultraviolet radiation penetrates deep into the atmosphere and destroys water molecules wherever it encounters them. The ultraviolet destruction process splits water molecules into hydrogen and oxygen atoms. Lightweight hydrogen escapes to space immediately. Heavy oxygen atoms fall back to the surface where they react with rocks and become permanently trapped as solid compounds. Venus ultraviolet exposure created a one-way water destruction system that operates continuously. Every water molecule that rises into the upper atmosphere gets destroyed by solar radiation. ensuring that the planet can never accumulate significant atmospheric water vapor. Goldilocks zone departure. The habitable zone around stars, the distance range where liquid water can exist on planetary surfaces, moves outward as stars grow brighter with age. Scientists call this the Goldilocks zone because planets must be not too hot, not too cold, but just right for life. Venus probably started within the habitable zone when the sun burned dimmer billions of years ago. As stellar brightness increased over time, the Goldilocks zone shifted farther from the sun. Venus got left behind in the increasingly hot inner region. Planets cannot follow the habitable zone as it migrates outward because gravitational forces lock them into fixed orbital distances from their parent stars. Once a planet falls out of the Goldilocks zone, it cannot move to stay within comfortable temperature ranges. Venus demonstrates that planetary habitability represents a temporary condition rather than a permanent state. Even planets that start in perfect locations can become uninhabitable when stellar evolution changes the energy conditions in their solar systems. Final solar engulfment. In approximately 5 billion years, our Sun will expand into a red giant star and literally swallow Venus whole. This represents the ultimate fate awaiting Venus regardless of how its current atmospheric conditions might change over time. Red giant expansion happens when stars exhaust the hydrogen fuel in their cores and begin burning helium in outer layers. This process causes massive stellar expansion that can grow stars to hundreds of times their original size. Our Sun will expand beyond Venus's orbital distance. Venus will vaporize completely when the expanding solar surface engulfs the planet's orbital path. The extreme temperatures inside a red giant star will instantly destroy every atom of planetary material. Nothing will remain of Venus except energy absorbed into the expanding star. This cosmic timeline puts Venus's current hellish conditions into perspective as a temporary phase in planetary evolution. The planet's atmospheric problems represent minor concerns compared to its inevitable complete destruction during solar expansion. Magnetic field absence vulnerability. Venus lacks the invisible magnetic shield that protects Earth from deadly space radiation and solar particle bombardment. This magnetic field acts like an invisible force field around planets that deflects harmful energy and particles from space. Earth's magnetic field creates a protective bubble extending thousands of miles into space. This magnetic shield redirects solar wind particles around our planet instead of letting them hit our atmosphere directly. The protection works automatically and continuously without requiring any energy input. Venus has almost no magnetic field strength compared to Earth's powerful protective system. Solar wind particles hit Venus' atmosphere directly with no magnetic deflection. The planet stands completely defenseless against space radiation that could sterilize any life forms. Venus demonstrates what happens when planets lose their primary defense system against space-based threats. Without magnetic protection, worlds become sitting targets for every form of deadly radiation and particle bombardment that space can deliver. Slow rotation dynamo suppression. Venus rotates so slowly that it cannot generate the electrical currents needed to create planetary magnetic fields. One Venus day lasts longer than an entire Venus year. The planet takes more time to spin once than to orbit the Sun completely. Planetary magnetic fields work like giant electrical generators powered by planetary rotation. Liquid metal in planetary cores must move fast enough to create electrical currents. These electrical currents generate magnetic fields that extend far into space around planets. Venus' rotation rate measures too slow to drive the electrical generator process in its molten iron core. The planet spins so gradually that liquid metal moves too slowly to create significant electrical currents. Without sufficient electrical activity, no magnetic field can form. This creates a permanent vulnerability that Venus cannot fix through any natural process. The planet's rotation rate has remained essentially constant for billions of years, ensuring that magnetic field generation remains impossible indefinitely. Selective atmospheric escape. Solar radiation strips away atmospheric gases based on their molecular weights, like a cosmic sorting machine that keeps heavy materials while discarding light ones. This selective removal process concentrates the most dangerous atmospheric components while eliminating potentially beneficial gases. Lightweight gases like hydrogen and water vapor escape easily when solar particles hit them. Heavy gases like carbon dioxide and sulfur dioxide resist removal and accumulate in the atmosphere. This creates atmospheric compositions dominated by the heaviest and most toxic molecules. Venus lost most of its light atmospheric gases to space, while retaining nearly pure concentrations of heavy greenhouse gases. The planet's atmosphere became increasingly dominated by carbon dioxide because lighter gases could not survive constant solar bombardment. The selective escape process explains why Venus developed such an extremely toxic atmospheric composition. Space radiation acted like a filter that removed everything except the most dangerous heat-trapping gases over billions of years. Direct solar wind atmospheric loss. Earth's magnetic field creates a protective barrier that deflects solar wind around our planet like water flowing around a rock in a stream. Venus has no such protection and absorbs the full impact of solar particle bombardment 24 hours a day. Solar wind consists of charged particles traveling at millions of miles per hour from the sun. These high-speed particles carry enough energy to knock atmospheric molecules completely away from planetary gravitational fields when they hit atmospheres directly. Venus' atmosphere faces continuous erosion from unblocked solar wind impacts. Every day, solar particles strip away atmospheric material that took millions of years to accumulate through geological processes. The planet loses atmosphere faster than natural processes can replace it. This represents a permanent atmospheric bleeding process that Venus cannot stop or reduce. The planet will continue losing atmospheric material to space as long as the sun produces solar wind and Venus lacks magnetic field protection. Ionosphere disruption acceleration. Venus' upper atmosphere becomes electrically unstable when solar radiation creates charged particles that cannot organize into stable patterns. Scientists call this region the ionosphere, where solar energy turns neutral gas molecules into electrically charged particles called ions. Earth's magnetic field organizes ionospheric electrical activity into stable patterns that help retain atmospheric gases. Venus has no magnetic organization system, so its ionosphere becomes chaotic and unstable. Electrical chaos accelerates the escape of atmospheric particles to space. Disorganized electrical activity in Venus' ionosphere works like a broken electrical system that short circuits and wastes energy. The chaotic electrical environment makes it easier for atmospheric particles to gain enough energy to escape planetary gravity completely. Venus ionospheric chaos represents an additional atmospheric loss mechanism that operates on top of direct solar wind erosion. The planet faces multiple simultaneous processes that all work together to strip away atmospheric material at accelerated rates. Hydrogen atoms cannot resist Venus's atmospheric escape processes because they represent the lightest element in the entire universe. These tiny atoms get knocked away from the planet much more easily than heavier atmospheric components. Venus water molecules break apart under intense solar radiation. When water splits into hydrogen and oxygen components, the hydrogen atoms immediately become vulnerable to escape. The lightweight atoms move much faster than heavy atoms at the same temperature. Atmospheric escape works like sorting materials by weight during a cosmic earthquake. Heavy objects stay put while light objects get shaken loose and fly away. Hydrogen atoms move so fast at Venus temperatures that planetary gravity cannot hold them effectively. This preferential hydrogen loss explains why Venus lost all its water permanently. Every time a water molecule got destroyed by solar radiation, the hydrogen component escaped to space, while the oxygen component remained trapped on the planet. High atmospheric temperatures give gas molecules enough energy to break free from planetary gravity completely. Venus' upper atmosphere reaches temperatures so extreme that many gas molecules move faster than the planet's escape velocity. Escape velocity represents the minimum speed needed for any object to leave a planetary gravitational field permanently. On Venus, intense atmospheric heating accelerates gas molecules beyond this critical speed threshold. The molecules literally race away from the planet like rockets launching into space. Thermal escape affects lighter molecules much more severely than heavy ones. At the same temperature, light molecules move much faster than heavy molecules. This creates preferential loss of lightweight atmospheric components while heavy gases remain bound to the planet. Venus atmospheric heating transformed normal gas molecules into high-speed escape vehicles that could overcome planetary gravity. The process operates continuously as long as upper atmospheric temperatures remain extreme enough to accelerate molecules beyond escape velocity. Venus surface rocks chemically capture oxygen atoms and lock them away permanently in solid mineral compounds. This process removes oxygen from the atmosphere just as effectively as if the gas had escaped to space completely. Chemical weathering on Venus works differently from Earth because of the extreme surface conditions. Hot rocks react aggressively with any oxygen that contacts them. Iron and other metals in Venus rocks oxidize rapidly, forming rust-like compounds that bind oxygen atoms permanently. These oxidation reactions create what chemists call irreversible chemical bonds, connections between atoms that cannot be broken apart under normal planetary conditions. Once oxygen gets incorporated into surface minerals, it becomes geologically trapped forever. Venus developed a planetary chemistry system that treats oxygen like a raw material for rock formation rather than an atmospheric gas. The planet's surface acts like a massive chemical factory that consumes atmospheric oxygen and converts it into solid mineral products. Venus originally contained a diverse mixture of atmospheric gases similar to other rocky planets during formation. Over billions of years, selective loss processes eliminated most gas varieties and concentrated the atmosphere into a few dominant components. Atmospheric simplification works like a natural sorting process that removes certain materials while concentrating others. Light gases escape to space. Reactive gases get absorbed by surface rocks. Only the most stable heavy gases persist in the atmosphere indefinitely. Modern Venus atmosphere consists almost entirely of carbon dioxide with trace amounts of nitrogen and sulfur compounds. This represents dramatic simplification from the complex atmospheric chemistry that probably existed during the planet's early history. The simplification process demonstrates how planetary atmospheres can evolve toward extreme chemical compositions through selective removal mechanisms. Venus lost atmospheric diversity and complexity while gaining concentration of the most persistent greenhouse gases. Scientists can determine which gases Venus lost to space by analyzing the atomic fingerprints left behind in the remaining atmosphere. Different versions of the same elements, called isotopes, escape at different rates and leave telltale evidence of atmospheric loss processes. Isotope analysis works like forensic science for planetary atmospheres. Light isotopes escape more easily than heavy isotopes of the same element. When selective escape occurs, the remaining atmospheric samples become enriched in heavy isotopes compared to original compositions. Venus' atmosphere contains isotope ratios that could only result from massive atmospheric loss over geological time. The heavy isotope concentrations prove that enormous quantities of lighter materials escaped to space while heavier materials accumulated. These isotopic signatures provide the strongest evidence that Venus underwent catastrophic atmospheric evolution rather than simply starting with its current extreme composition. The atomic fingerprints reveal a history of selective atmospheric destruction that transformed the planet's chemical environment completely. Hell, Earth's successful evolution. Earth operates multiple planetary life support systems simultaneously to maintain perfect conditions for liquid water and biological activity. Our planet combines the right distance from the Sun with protective magnetic fields and stable atmospheric composition. Earth's oceans absorb excess carbon dioxide from the atmosphere like giant sponges that prevent greenhouse gas accumulation. Plate tectonics recycles surface materials and releases just enough volcanic gases to maintain moderate atmospheric greenhouse effects. The magnetic field deflects harmful solar radiation. These systems work together like a perfectly tuned orchestra, where each instrument plays its part to create harmonious results. Ocean currents distribute heat globally. Atmospheric circulation patterns moderate temperature extremes. Biological processes help regulate gas concentrations. Earth demonstrates that successful planetary evolution requires multiple protective systems working in coordination. The planet achieved the delicate balance between competing forces that Venus lost and Mars never developed. Opposite direction extreme. Mars lost its atmosphere and became too cold for liquid water, while Venus retained too much atmosphere and became too hot for any water at all. These sister planets followed completely opposite evolutionary paths toward equally hostile environments. Mars represents the cold extreme of planetary climate failure. The planet's small size meant weak gravity that couldn't hold onto atmospheric gases effectively. Loss of atmospheric greenhouse effect caused surface temperatures to plummet far below the freezing point of water. Mars also lost its magnetic field protection much earlier than Venus. Solar winds stripped away the planet's thin atmosphere over billions of years. Without sufficient atmospheric insulation, Mars' surface became as cold and barren as Antarctica in permanent winter. The comparison reveals that planetary habitability exists in a narrow zone between two extreme failure modes. Planets can die by freezing just as easily as they can die by overheating, depending on their specific characteristics and evolutionary history. Trapping. Greenhouse effect spectrum. Venus, Earth, and Mars demonstrate the complete range of possible greenhouse effects that rocky planets can achieve. Mars has too little greenhouse warming. Earth has just the right amount. Venus has catastrophically too much. Greenhouse effects work like planetary thermostats that can be set anywhere from freezing cold to molten hot. Mars' atmospheric thermostat got stuck on the coldest setting. Earth's thermostat maintains moderate temperature. Venus' thermostat broke and got stuck on maximum heat. The 3 planets prove that greenhouse effects represent the most important factor, controlling planetary surface temperatures. But distance from the Sun matters less than atmospheric composition when determining whether worlds become habitable or hostile. This greenhouse spectrum shows that atmospheric evolution can push planets toward any temperature extreme regardless of their starting conditions. 3 similar rocky worlds achieved completely different climate outcomes through different atmospheric evolutionary pathways. Specific characteristics: distance versus intrinsic characteristics. Orbital distance from the Sun establishes initial planetary conditions, but each planet's unique characteristics determine its ultimate evolutionary fate. Venus and Earth started in similar solar energy zones but developed completely different atmospheric systems. Planet-specific factors include rotation rate, magnetic field strength, atmospheric chemistry, geological activity, and gravitational field strength. These intrinsic characteristics influence atmospheric evolution more powerfully than simple distance considerations. Mars sits farther from the Sun than Earth, but lost its atmosphere through internal factors rather than solar distance effects. Venus sits closer to the Sun than Earth, but developed extreme conditions through runaway atmospheric processes rather than just solar heating. The comparison demonstrates that planetary habitability depends more on complex internal evolutionary processes than on simple astronomical positioning. Distance provides the starting energy budget, but planetary characteristics control the final climate outcome. Independent fate. Venus and Earth have nearly identical sizes but achieved opposite climate outcomes, while Mars has a different size and achieved a third completely different result. Planet size alone cannot predict whether worlds will become habitable or hostile. Size affects important planetary characteristics like gravitational strength, magnetic field generation capability, and geological activity levels. However, the Venus-Earth comparison proves that similar-sized worlds can follow completely different evolutionary pathways. Mars demonstrates that smaller planets face different challenges than larger ones, including weaker gravity for atmospheric retention and reduced geological activity. Yet size represents just one factor among many that influence planetary evolution. The 3-planet comparison reveals that planetary fate depends on complex interactions among multiple characteristics rather than any single factor like size, distance, or initial composition. Similar starting conditions can produce dramatically different final results through the butterfly effect of planetary evolution. Soviet Venera spacecraft achieved the impossible by landing on Venus' surface and transmitting data back to Earth before the extreme conditions destroyed them completely. These robotic explorers survived in conditions that would melt most metals within minutes. How do you design a spacecraft to survive on the surface of hell itself? Soviet engineers created heavily armored probes that could withstand crushing atmospheric pressure and molten lead temperatures. The spacecraft used cooling systems and reinforced hulls like deep-sea submarines designed for the ultimate depths. The Venera missions proved that human technology could reach Venus' surface and gather scientific data despite the planet's efforts to destroy any visiting hardware. These landing achievements required engineering solutions for the most extreme environmental conditions known in our solar system. Venera spacecraft made history as the first human-built objects to successfully operate on another planet's surface and report their findings. The missions demonstrated that determined engineering could overcome even the most hostile planetary environments for brief but scientifically valuable periods. The Magellan spacecraft solved the problem of mapping Venus by using radar technology that can penetrate thick atmospheric layers like X-rays seeing through human bodies. Visible light cannot pierce Venus's dense cloud cover, but radio waves pass through easily. Radar mapping works like echolocation that dolphins and bats use to navigate in dark environments. The spacecraft sends radio signals toward the planet's surface. The signals bounce back carrying information about surface features, elevation changes, and geological structures. Magellan created the most detailed maps ever made of Venus' surface by methodically scanning every square mile of the planet over multiple years. The radar revealed massive volcanic features, impact craters, and geological formations that no optical telescope could ever observe. This radar mapping technology proved that thick planetary atmospheres cannot prevent detailed surface exploration when the right scientific instruments are used. Magellan demonstrated that human ingenuity could expose the secrets of even the most well-hidden planetary surfaces. Pioneer Venus spacecraft discovered that Venus' atmosphere contains multiple layers with completely different environmental conditions stacked on top of each other like floors in a skyscraper of hell. Each atmospheric level presented unique challenges and characteristics. Scientists needed detailed atmospheric measurements to understand how Venus' greenhouse effect operates at different altitudes and pressures. Pioneer Venus carried instruments that could analyze temperature, pressure, and chemical composition throughout the entire atmospheric column. The mission revealed the shocking discovery that Venus' atmospheric structure defies normal planetary expectations. Surface conditions reach furnace temperatures, while upper atmospheric zones maintain relatively pleasant conditions comparable to Earth's climate. Pioneer Venus provided the fundamental atmospheric data that scientists needed to understand Venus's extreme greenhouse effect mechanisms. The mission proved that planetary atmospheres can create much more complex vertical environmental structures than anyone had imagined possible. Venera atmospheric chemistry measurements confirmed that Venus air contains the most toxic combination of gases found anywhere in our solar system. The probes identified sulfuric acid concentrations that would dissolve most materials within seconds of exposure. Chemical analysis required specialized instruments that could survive long enough in the corrosive environment to gather accurate measurements. Venera probes carried protected sensors that could analyze gas composition while being constantly attacked by acid vapors. The measurements proved that Venus' atmosphere represents a perfect storm of toxic chemistry that makes the planet completely hostile to any form of life. Carbon dioxide dominates the atmospheric composition, while sulfuric acid creates the most corrosive environment known to science. Venera chemical analysis provided the definitive evidence that Venus' atmospheric composition results from runaway geological and chemical processes rather than simple solar heating. The missions confirmed that Venus transformed into a chemical hell through its own internal atmospheric evolution. One probe accomplished one of the most dangerous scientific missions ever attempted by deliberately flying through Venus's sulfuric acid cloud layers to measure their internal chemistry directly. This represented the equivalent of flying a research aircraft through concentrated battery acid. What happens inside acid clouds that can dissolve metal spacecraft within hours? The mission carried specially protected instruments that could analyze cloud chemistry while being constantly attacked by corrosive droplets that would destroy normal materials instantly. The probe survived its passage through the acid cloud factory long enough to measure the chemical processes that create and maintain Venus's permanent sulfuric acid production system. These direct measurements revealed the detailed chemistry behind Venus's most deadly atmospheric feature. This mission proved that human scientific curiosity could overcome even the most extreme environmental hazards through careful engineering and protective technology. The mission demonstrated that no planetary environment is too hostile to prevent scientific exploration when proper precautions are taken. Venus' atmosphere presents an impossible challenge for computer climate models because the planet operates two completely different wind systems simultaneously. Surface winds barely move while upper atmospheric winds race around the globe at incredible speeds. Scientists use three-dimensional climate models, computer programs that create virtual versions of planetary atmospheres inside digital environments. These virtual atmospheres follow the same physical laws that govern real planetary weather systems. The computers calculate how gases move under different temperature and pressure conditions. Creating a digital twin of Venus' atmosphere required solving the mystery of how two opposite wind systems can coexist on the same world. The models had to reproduce nearly motionless surface conditions while simultaneously generating hurricane-speed upper atmospheric circulation. Computer simulations finally cracked the Venus atmospheric code by revealing the physical mechanisms that create this bizarre dual-layer wind structure. The models proved that extreme atmospheric density differences between surface and upper levels create isolated wind zones that operate independently. Climate scientists run computer simulations backward through time like digital archaeology that reconstructs Venus's atmospheric history from billions of years ago. These computational time machines test different possible pathways that could have led to current conditions. Reverse climate modeling works like solving a crime by working backward from the evidence at the crime scene. Scientists start with Venus's current extreme atmospheric composition and run computer models in reverse to identify what earlier conditions could have produced these results. The computer models test thousands of different evolutionary scenarios to find which pathways successfully reproduce Venus's observed atmospheric characteristics. Each simulation represents a different possible history that the planet might have experienced over geological time. These digital archaeological investigations revealed the critical tipping points where Venus atmospheric evolution became irreversible. The computer time machines identified the specific thresholds that pushed Venus past the point where normal planetary climate regulation systems could function. Computer models calculate exactly how long it took Venus to lose all its water by simulating the step-by-step destruction of planetary oceans over geological time scales. These digital timekeepers track molecular processes that operate too slowly for human observation. Water loss modeling works like creating a computer simulation of an extremely slow-motion disaster movie. The models track individual water molecules as they evaporate into the atmosphere, get destroyed by solar radiation, and have their components escape to space or react with surface rocks. Scientists discovered that Venus water loss happened much faster than anyone expected when computer models revealed the acceleration effects of runaway atmospheric heating. The planet lost its oceans in millions rather than billions of years once critical temperature thresholds were exceeded. These computational stopwatches proved that planetary water loss represents a rapid catastrophe rather than a gradual process when atmospheric conditions cross certain critical boundaries. Venus demonstrates how quickly planets can transform from potentially habitable to completely sterile. Venus's sulfuric acid cloud formation involves chemical reactions so complex that only computer models can track all the simultaneous processes happening throughout the entire atmospheric system. These virtual chemistry laboratories simulate millions of chemical reactions occurring at different altitudes simultaneously. Computer chemistry models work like digital laboratories where scientists can perform experiments that would be impossible in real chemistry labs. The models simulate how sulfur compounds from volcanic activity interact with water vapor and solar radiation to create sulfuric acid clouds. Virtual chemistry experiments revealed the precise atmospheric conditions needed to maintain Venus's permanent acid cloud production system. The models identified the altitude ranges, temperature zones, and chemical concentration levels that keep the acid cloud factory operating continuously. Computer simulations proved that Venus developed the perfect chemical storm for sustained acid production through a combination of geological activity and atmospheric chemistry that creates self-sustaining toxic cloud formation cycles. Climate scientists use computer models to predict Venus's future atmospheric evolution as the Sun continues growing brighter over billions of years. These digital fortune tellers calculate how Venus conditions will change as stellar evolution increases the energy input to the planet. Future climate modeling works like creating computer simulations of planetary destiny that extend billions of years into the future. The models incorporate solar evolution predictions with current Venus atmospheric behavior to forecast long-term planetary changes. Computer predictions reveal that Venus atmospheric conditions will become even more extreme as solar energy output increases over geological time. Surface temperatures will rise further while atmospheric pressure continues building to even more crushing levels. These computational crystal balls demonstrate that Venus represents a planet trapped in permanent atmospheric degradation with no possibility of natural improvement. The future modeling confirms that Venus will become increasingly hostile until the Sun eventually expands and destroys the planet completely. Throughout the galaxy, exoplanet Venus-type discovery. Telescopes discover Venus-like planets around other stars with disturbing regularity. These exoplanets, planets orbiting stars other than our Sun, show the same deadly characteristics that make Venus uninhabitable. Rocky planets close to their parent stars frequently develop extreme greenhouse effects. Exoplanet detection works like stellar detective work, where astronomers analyze starlight for clues about orbiting worlds. When planets pass in front of their stars, they create tiny eclipses that reveal planetary sizes and orbital distances. Additional measurements can determine atmospheric composition and surface temperatures. The discoveries reveal that Venus-type atmospheric catastrophes happen commonly throughout our galaxy rather than representing rare cosmic accidents. Many rocky planets that orbit too close to their stars develop runaway greenhouse effects and become hellish worlds. Venus represents a typical example of planetary climate failure rather than an unusual case in our solar system. The universe contains countless worlds that followed similar evolutionary pathways toward permanent atmospheric catastrophe. Paradise planets in our galaxy, hot Earth-type universality. Kepler Space Telescope data shows that hot rocky planets like Venus appear much more frequently than temperate Earth-like worlds throughout our galaxy. The universe seems to favor creating hell planets over paradise planets when rocky worlds form close to their parent stars. Statistical analysis of thousands of exoplanet discoveries reveals disturbing patterns about planetary habitability. Rocky planets that receive high stellar energy input almost always develop extreme atmospheric conditions. Earth-like temperate conditions represent the exception rather than the rule. The frequency data suggests that runaway greenhouse effects occur naturally when rocky planets exceed certain energy thresholds from their parent stars. Venus-type atmospheric evolution appears to be the default outcome for most rocky worlds that orbit within certain distance ranges. These statistics indicate that habitable planets represent rare cosmic treasures while hellish worlds dominate the galaxy. The universe operates like a planetary factory that produces far more failures than successes when creating potentially habitable worlds. Poisonous atmospheres from thousands of light years away. Exoplanet extreme greenhouse detection. Astronomers identify Venus-type atmospheres around distant exoplanets by analyzing the specific wavelengths of light that pass through planetary atmospheres when the planets eclipse their parent stars. Each atmospheric gas absorbs different colors of starlight like chemical fingerprints. Atmospheric spectroscopy works like analyzing blood samples to identify diseases, except astronomers analyze starlight to identify atmospheric composition. Carbon dioxide, water vapor, and other greenhouse gases each absorb specific wavelengths of light that create recognizable patterns in stellar spectra. Remote detection reveals that many exoplanets possess atmospheric compositions similar to Venus with extreme carbon dioxide concentrations and evidence of runaway greenhouse heating. These atmospheric signatures can be detected across interstellar distances without requiring spacecraft visits. Spectroscopic analysis proves that Venus-type atmospheric conditions exist commonly throughout the galaxy and can be identified reliably using current astronomical technology. Distance presents no barrier to detecting the atmospheric fingerprints of planetary climate disasters. Support life or represent death traps. Life Possibility Complex Assessment (TUNG). Scientists once believed that measuring a planet's distance from its parent star could determine habitability. Planets in the Goldilocks zone would be just right for life, while planets outside this zone would be too hot or too cold. Venus proves this simple approach dangerously wrong. Planetary habitability depends on complex interactions among atmospheric composition, magnetic field strength, geological activity, and stellar evolution rather than just orbital distance. Venus sits near the edge of our solar system's habitable zone, but developed hellish conditions anyway. Exoplanet habitability assessment now requires analyzing dozens of different factors, including atmospheric chemistry, planetary mass, magnetic field indicators, and stellar characteristics. Distance alone provides insufficient information to determine whether worlds support life or represent death traps. The Venus lesson forces astronomers to develop much more sophisticated methods for evaluating exoplanet habitability that consider the complex planetary evolution processes that determine long-term atmospheric stability. Extraterrestrial intelligence, CTI exclusion criteria. CTI researchers, scientists searching for extraterrestrial intelligence, use Venus-type atmospheric characteristics to eliminate exoplanets from their target lists. Worlds with extreme greenhouse effects cannot support technological civilizations regardless of their other characteristics. The search for extraterrestrial intelligence requires focusing limited resources on planets that could actually harbor life and technology. Including Venus-type hell planets in SETI surveys wastes valuable telescope time that could be spent analyzing potentially habitable worlds. Atmospheric composition analysis allows SETI researchers to create exclusion criteria that automatically eliminate exoplanets with Venus-like carbon dioxide concentrations and extreme surface temperatures. These screening methods help focus searches on worlds with better habitability prospects. Venus provides a perfect example of planetary conditions that definitively exclude worlds from consideration in the search for extraterrestrial life and intelligence. Hell planets cannot produce the stable long-term conditions necessary for biological evolution and technological development. Future engineering projects could potentially remove carbon dioxide from Venus' atmosphere through massive industrial operations that dwarf any technology humans have ever built. These hypothetical atmospheric processing systems would need to operate on planetary scales for thousands of years. Atmospheric carbon dioxide removal works like running a giant air purification system that processes entire planetary atmospheres instead of cleaning single rooms. The machinery would need to capture greenhouse gases from Venus' atmosphere and either convert them to solid materials or launch them away from the planet completely. Current human technology cannot approach the scale needed for Venus atmospheric cleanup operations. The planet contains roughly 1 million times more carbon dioxide than Earth's entire atmosphere. Removing this quantity would require industrial capacity that exceeds human civilization's total energy production. Venus atmospheric engineering represents the ultimate test of whether advanced technological civilizations can reverse planetary-scale environmental catastrophes. The challenge exceeds current human capabilities by factors that make interplanetary travel seem simple by comparison. Scientists cannot design space-based solar shields large enough to reduce Venus' surface temperatures through solar radiation blocking. The engineering challenges exceed anything humans have attempted in space construction projects. Solar radiation shields would need to cover areas larger than entire continents while maintaining stable positions between Venus and the Sun. These structures would require materials that can withstand continuous solar radiation bombardment while remaining mechanically stable across interplanetary distances. The shield installations would need to reduce solar energy reaching Venus by approximately 50% to enable atmospheric cooling. This requires blocking surfaces with dimensions measured in thousands of miles. Construction projects that exceed human space engineering experience. Venus cooling through solar radiation management remains beyond human technological capabilities for the foreseeable future. The scale requirements represent engineering challenges comparable to dismantling and rebuilding entire moons. Venus' upper atmosphere offers the most Earth-like conditions found anywhere else in our solar system outside of Earth itself. At 50-mile altitude, temperature and atmospheric pressure approximate conditions that humans could survive with basic life support systems. Atmospheric habitation would work like building floating cities that hover permanently above Venus cloud layers. These aerial settlements would use buoyancy principles, the same physics that keep hot air balloons aloft, to maintain stable positions in the upper atmosphere. The floating habitat concept avoids all the deadly surface conditions that make Venus exploration impossible while taking advantage of relatively benign upper atmospheric conditions. Residents could conduct scientific research and resource extraction without facing the crushing pressure and molten temperatures below. Venus atmospheric colonization represents the most realistic approach to human presence on the planet because it exploits the only environmental zone where human technology can function effectively for extended periods. Scientists study extremophile microorganisms, bacteria that thrive in harsh environments like boiling hot springs and acidic volcanic vents, as potential biological tools for Venus atmospheric engineering. These organisms could theoretically be modified to consume carbon dioxide and produce oxygen. Biological terraforming works like planting microscopic gardens throughout planetary atmospheres where specially designed bacteria consume atmospheric pollutants and produce beneficial gases. The microorganisms would function as living atmospheric processing factories that reproduce themselves automatically. Genetically engineered bacteria designed for Venus conditions would need to survive extreme heat, crushing pressure, and sulfuric acid environments while performing useful atmospheric chemistry. Creating such organisms requires biotechnology advances that push the boundaries of genetic engineering. Microbial atmospheric modification offers theoretical advantages over mechanical engineering approaches because biological systems can self-replicate and adapt to changing conditions automatically. However, the required genetic modifications exceed current biotechnology capabilities significantly. Venus terraforming represents the most ambitious engineering project humans could theoretically attempt, requiring energy resources and time scales that exceed entire civilizations. The project difficulty makes building pyramids look like children's sandbox construction. Energy calculations reveal that Venus atmospheric modification would consume more power than human civilization has generated throughout all of recorded history. The project would require sustained industrial capacity operating continuously for thousands of years without interruption. Time requirements extend beyond the lifespan of empires and technological civilizations. Venus terraforming timelines stretch longer than the period from ancient Egyptian pyramids to modern space exploration. No human institution has maintained consistent technological capability across such extended periods. Venus atmospheric engineering remains scientifically possible but practically impossible given current human technological and organizational capabilities. The planet will likely remain a hellish world indefinitely because the solutions exceed human civilization's capacity to implement them. Vulnerabilities. Extreme case insight provision. Venus research provides Earth climate scientists with the ultimate medical case study that shows how greenhouse effects can destroy entire planetary environments. Just like doctors study extreme disease cases to understand normal health conditions, climate scientists analyze Venus to understand Earth's climate vulnerabilities. Extreme case analysis works like studying patients with severe heart disease to understand how healthy hearts can fail when stressed beyond their limits. Venus represents the most extreme example of atmospheric heart failure that helps scientists identify the warning signs before planetary climate systems collapse. Venus atmospheric evolution reveals the long-term consequences of unchecked greenhouse gas accumulation that would take millions of years to observe on Earth directly. The planet serves as a time-lapse movie showing how small atmospheric changes can escalate into planetary environmental collapse. This extreme case study provides Earth climate researchers with crucial insights about the ultimate dangers of atmospheric greenhouse gas accumulation that no Earth-based research could reveal. Venus functions as our solar system's most important climate change laboratory. Climate change becomes unstoppable. Critical Point Preventive Policy, or scientists study Venus to identify the specific atmospheric thresholds that trigger runaway greenhouse effects on rocky planets. Understanding these critical tipping points helps Earth policymakers recognize how close our planet might come to irreversible climate transformation. Atmospheric tipping points work like the moment when a balanced scale tips over and cannot return to its original position. Small additional weights on one side can suddenly cause the entire system to flip permanently in one direction with no possibility of returning to balance. Venus crossed multiple atmospheric tipping points that made its climate transformation permanent and irreversible. Research identifies the atmospheric gas concentrations and feedback mechanisms that pushed Venus beyond the point where natural cooling processes could function. Earth climate policy requires understanding these critical thresholds to prevent our planet from approaching the same atmospheric conditions that destroyed Venus's habitability. The planet serves as the ultimate cautionary tale about the permanent consequences of atmospheric neglect. Policy against atmospheric disasters. Ocean carbon absorption importance alerts. Ocean carbon absorption prevents Earth from developing Venus-type atmospheric conditions by removing excess greenhouse gases before they can accumulate to dangerous levels. Earth's oceans function like massive atmospheric insurance policies that protect against climate catastrophe. Ocean carbon absorption works like having emergency flood drainage systems that prevent water from accumulating to dangerous levels during storms. When too much carbon dioxide enters Earth's atmosphere, oceans absorb the excess before it can trigger runaway heating effects. Venus lost its oceans and therefore lost the primary planetary mechanism for controlling atmospheric carbon dioxide concentrations. Without oceanic carbon absorption, Venus' atmosphere accumulated greenhouse gases until it reached catastrophic levels that could never be reduced. Earth's oceanic carbon absorption system represents the most important climate protection mechanism our planet possesses. Venus demonstrates what happens when planets lose this crucial atmospheric regulation service that prevents greenhouse gas accumulation disasters, unless feedback systems amplify them into planetary catastrophes. Feedback risk learning. Venus teaches Earth scientists that apparently small atmospheric changes can trigger massive climate transformations when feedback mechanisms amplify the initial changes. These feedback systems work like sound amplifiers that turn whispers into deafening noise. Climate feedback loops operate like domino chains where knocking over one small piece triggers increasingly larger pieces to fall in sequence. Venus experienced feedback amplification that transformed minor atmospheric adjustments into planetary climate catastrophe through self-reinforcing processes. The planet's climate evolution reveals how feedback mechanisms can overwhelm natural climate regulation systems when atmospheric conditions exceed certain thresholds. Small increases in greenhouse gases triggered feedback processes that produced enormous additional greenhouse effects. Earth climate systems contain similar feedback mechanisms that could potentially amplify small atmospheric changes into much larger climate disruptions. Venus serves as the ultimate example of how feedback amplification can transform manageable climate changes into uncontrollable planetary transformation. Changes cannot be reversed even with unlimited time and technology. Climate irreversibility lessons GOC. Venus atmospheric research reveals that certain planetary climate changes represent permanent transformations that cannot be undone regardless of how much time passes or what technology might be applied. Some environmental damage exceeds the limits of natural or artificial repair capabilities. Irreversible climate change works like certain medical conditions that cause permanent damage to vital organs, even when the original disease gets cured. Venus' atmosphere underwent chemical and physical changes so extreme that the planet cannot return to Earth-like conditions. The planet crossed multiple irreversibility thresholds where atmospheric processes became self-sustaining and immune to external cooling influences. Venus climate change represents the ultimate example of environmental transformation beyond the reach of any restoration efforts. These irreversibility lessons force Earth climate policy to focus on prevention rather than cure because certain atmospheric changes cannot be fixed once they occur. Venus proves that some planetary environmental damage represents permanent loss that no future technology could repair. How do you predict the future of systems where butterfly wings can trigger hurricanes? Venus evolution demonstrates that planetary climates represent complex systems. Scientific environments where small initial differences can produce completely different final outcomes through unpredictable chains of cause and effect. Complex systems analysis works like trying to predict exactly where a pinball will end up after bouncing through a machine full of obstacles. Scientists can understand the basic physics that governs planetary evolution, but they cannot predict specific outcomes when tiny variables can amplify into enormous differences. Venus and Earth started with nearly identical conditions, yet achieved opposite climate results through complex system evolution. The planets followed different pathways through atmospheric development, where minor variations in timing, chemistry, or geological activity created dramatically different final states. Complex systems research reveals that planetary climate evolution contains inherent unpredictability limits that prevent precise long-term forecasting. Venus proves that even scientists who perfectly understand physical laws cannot predict specific planetary futures when complex system effects dominate evolutionary processes. Venus' atmospheric development followed strict physical laws while simultaneously experiencing random events that influenced the planet's evolutionary pathway. The combination of deterministic processes and chance occurrences created Venus's unique climate history that could not be repeated exactly. Planetary evolution works like playing poker, where players follow definite rules while dealing with random cards that determine specific game outcomes. Physical laws govern how atmospheric processes operate, but random events determine which processes activate when and where. Chance events that affected Venus evolution include the timing of major volcanic eruptions, asteroid impacts, and changes in solar radiation patterns. These random influences worked within the constraints of physical laws to push Venus toward its current extreme atmospheric state. Venus climate evolution demonstrates that planetary destinies result from the intersection of predictable physical processes with unpredictable cosmic circumstances. The planet's atmospheric transformation required both inevitable physical laws and specific random events that happen to occur at critical moments. Venus discoveries cannot fit into simple habitability definitions based only on distance from parent stars and surface temperature ranges. The planet demonstrates that long-term atmospheric stability and evolutionary pathways matter more than initial conditions for determining whether worlds can support life. Traditional habitability assessment worked like judging books by their covers. Scientists assumed that planets with the right size and location would automatically develop suitable conditions for life. Venus proves this approach fundamentally inadequate for evaluating planetary habitability potential. Modern habitability science must consider atmospheric chemistry, magnetic field evolution, geological activity patterns, and long-term climate stability in addition to basic physical characteristics. Venus shows that planets can start in habitable zones but evolve into hellish conditions through internal processes. This habitability redefinition forces scientists to develop much more sophisticated methods for evaluating whether exoplanets could actually support life, rather than simply measuring their distance from parent stars. Venus revolutionized the scientific understanding of what makes planets truly habitable. Venus-type climate catastrophes might represent the normal outcome for rocky planet evolution, while Earth-type stable climates represent extremely rare cosmic accidents. The universe could contain mostly failed planets with only occasional successful worlds that maintain habitable conditions. Cosmic probability analysis works like studying lottery results, where winning tickets appear much less frequently than losing tickets. Venus demonstrates that planetary climate evolution contains many more pathways toward atmospheric failure than toward long-term climate stability. Statistical analysis of rocky planet formation suggests that Venus-type atmospheric evolution represents the default outcome when multiple factors must align perfectly for planets to maintain habitable conditions. Earth's successful climate evolution might require an extremely unlikely combination of favorable circumstances. This rarity hypothesis forces scientists to consider that Earth represents an extraordinarily fortunate exception rather than a typical example of planetary evolution. Venus demonstrates that the universe might be filled primarily with failed worlds where atmospheric evolution produced uninhabitable conditions. Venus research reveals that natural systems can exceed the prediction capabilities of even the most advanced scientific methods and computer models. The planet's complex atmospheric evolution demonstrates fundamental limits to human scientific forecasting that cannot be overcome through improved technology. Scientific humility means recognizing that nature operates through processes too complex for complete human understanding and prediction. Venus atmospheric development involved interactions among so many variables that precise prediction remains impossible even when scientists understand the individual physical processes. Complex natural systems like planetary climates can surprise scientists despite decades of intensive research and sophisticated computer modeling. Venus continues to reveal unexpected atmospheric behaviors that force scientists to revise their theories about planetary evolution. Venus forces the scientific community to acknowledge that nature contains mysteries that exceed human analytical capabilities, regardless of technological advancement. The planet serves as a permanent reminder that scientific knowledge has inherent limits when confronted with the full complexity of natural systems.